All right, so this is Math 150, Section 1 lecture. I have no idea anymore. It's been too long since we've had a lecture recorded. So what I want to do today is I want to start talking about ways to integrate. So in Calc 1, we have a couple of techniques. We have trig substitution, we have U substitution, we have the most hated method of all, which is?
Integration by parts?
No. We love integration by parts. No. You're not allowed to say you hate integration by parts. That's too good of a method. The most hated.
Trig sub?
I'm sorry?
Trig sub?
No, there's something worse than trig. I think trig substitution comes in at number 2. Partial fractions. Usually partial fractions is the one that people hate the most. But it turns out to be very useful for other things. In multivariable calculus, we now have to do double integrals, triple integrals. What techniques do we have? The really big ones are the change of variables, especially for polar, cylindrical, and spherical, and changing order of integration. So in terms of trying to figure out what should you do, basically almost when we do a decision tree. Let me try to do the integral as is. Can I do it? If yes, do it. If I can't do it, then let me try various things. Let me try switching orders of integration. And as long as the double integral of the absolute value is finite, you can switch orders. If that is working, great. If it's not working, try something else. Try changing variables. After a while, you start to detect which one should you do first. If you can see a very nice antiderivative, it's probably a good idea to do it as is. If it looks like it has radial symmetry, probably polar or spherical coordinates is the way to go. And after a while, you can do it a lot faster. This is very similar to looking at a quadratic, and can you just see the factors? Can you see how to factor it? The more of these you do, the better you are at it. Okay? Now, whenever you have a homework problem, almost surely one of these techniques will be useful. If it is from the section on spherical coordinates, I think it's pretty clear what you should try to use for that section. On exams and on life, it's much harder because you don't necessarily know what you should use. One of the big things is always to sketch the region of integration. So what I want to do is I want to start with an integral. So I will integrate y goes from 0 to 2, x goes from y half to 1, y e to the x cubed dx dy. So for those of us who are visiting for the first time and thrown into multivariable calculus, what this means is first integrate this function, treating y as a constant. If you want to search and replace, put in pi, wherever you see y, put in 17, favorite number. Integrate this, and then when you're done, integrate with respect to y. In one variable calculus, we often don't put subscripts on the integrals. We do it here so that we really remember which way we should do things. All right, so here's a nice integral to do. I don't mean nice as in this is going to be easy to do. I mean this is good for illustrative purposes. First thing is to try to do it as given. All right, so I need to find a function when I integrate with respect to x, which will be nice, and whose derivative with respect to x will then be y e to the x cubed. Well, y is a constant, right? Because I'm integrating with respect to x, so the y doesn't really matter. So I want an f of x such that big F prime of x is e to the x cubed. And unfortunately, there is no nice function whose derivative is e to the x cubed. So what this tells us, we cannot do the integration as stated. So we need to switch orders of integration, or we need to do a change of variables. We haven't really covered change of variables yet. And also, this doesn't seem to have any nice change going around. There's no radial symmetry or something. So the first thing we should do is we should plot the region. So y goes from 0 to 2, x goes from y halves to 1. So I can tell from this that I'm integrating over a part in the upper right quadrant. So here's my x-axis, here's my y-axis. Y starts at 0 and ends at 2. And then the value of x goes from y halves all the way to 1. Okay, so that's nice. No matter what value of y I start with, I always end at x equals 1. And for a given value of y, where do I start x? I start at y over 2. So when y equals 2, where do I start?
X equals 1.
X equals 1. So, okay, when x equals 0, when y equals 0, I start at 0. When y equals 1, I would start at 1/2. And so you can see basically my region of integration is going to be a triangle. I always go from one of these points to the line x equals 1. So I'm integrating over a triangle. And because I'm doing y is fixed first, and then x goes from y/2 to 1, I'm going in this direction. Because the integration isn't looking nice, maybe I should try going the other way. Fix x, and then have y go from what to what. So here's x, here's y, and so now I would be going upwards. So what is this line here? This line is the line x equals y/2. And given a value of y, I have a value of x. I now want to write it the other way. I want to write not x as a function of y, but y as a function of x. This is fortunately not too bad. This is the same as y equals 2x. And so this integral is going to be the same as x goes from something to something, y goes from something to something, y e to the x cubed dy dx. Right? X is going to go from 0 to 1. And now what is y going to go? Y is always going to start at 0. And y goes all the way up to 2x. Okay. So now we want to find a function whose derivative with respect to y is y. All right, what would that be? Y squared over 2. So we now get the integral. X goes from 0 to 1. Then we would have e to the x cubed. We would have y squared over 2 evaluated 0 and 2x dx. When I evaluate this at 0, I get 0. When I evaluate it at 2x, I get 4x squared over 2. So I get 2x squared. So we are left with the integral. X goes from 0 to 1. E x cubed. Then I would have 2x squared dx. This is almost what you would hope for, right? Instead of a 2x squared, what would you like to have? 3x squared. Then we could do a u substitution. So what I want to do is I want to multiply by 3 over 3. I'll pull out a 2. This is going to be the same as 2/3 integral x goes from 0 to 1 e to the x cubed 3x squared dx. And now if we do a u substitution, let's say u equals this. Two different ways you could do the u substitution. How do you want to do the u substitution? What are the two ways we could do u substitution? So we have visitors. This is fair game for you because you're taking calculus. What are the two ways we could do u substitution? You have two choices. What's one way? Yes?
U is x cubed.
So one is u is x cubed. What's the other way? Yes?
E to the x.
Yeah, the other one could be e to the x cubed. So we could try that. One of the ways is not going to work as well. If we tried u was e to the x cubed, then its derivative would be e to the x cubed 3x squared dx. So in fact, we would just have du. So it does work actually. I prefer, I think, doing u equals x cubed, but you could actually do it as e to the x cubed as well. You would just have, the integration would just become du. So u is x cubed, du is 3x squared dx. X goes from 0 to 1, so u goes from 0 to 1. So we get, 2/3, u goes from 0 to 1, e to the u du. So we get 2/3 e to the u at 0 and 1. So we get 2/3 e minus 2/3, or 2/3 e minus 1. So as always, whenever we have something like this, we want to check at the end of the day and see, is this reasonable? Well, what can you tell me about this function? Y e to the x cubed. What kind of values does it take on? So So what kind of numbers is y e to the x cubed?
Positive number.
I'm sorry?
It's a positive number.
It's a positive number. So we should definitely not be getting a negative value for the integral because we're integrating a positive number. Okay, what's the largest value we'll take on? So when you look at the range we're going from, y goes from 0 to 2, x goes from 0 to 1. What's the largest value you could take? Yes?
2e.
2e. It's not going to be larger than 2e, so it's at most 2e. What's the area of the triangle?
1.
1. Its base is 1, its height is 2, so area of triangle is 1, so integral will be less than equal to 2e. And we see quite clearly that our integral is less than 2e. So, this doesn't prove we did it right, but it at least proves that what we have is reasonable. Okay? This is a cookbook problem. It was clearly designed to have an integration that is not nice with respect to the order given. And so if you are struggling, if you are having trouble finding the antiderivative, try looking at it the other way. Okay, any questions about this problem? Okay. So I want to motivate why we're going to spend so much time doing the change of variable formula. When I was a freshman in college, we had some extra time at the end of the second semester in a great integrated year-long course, and the professors started proving the change of variable formula in as great generality as possible. I can check my notes. Unfortunately, they may be in storage for 3 years. I believe we used every letter of the English alphabet, most of the Greek letters, and I think 1 or 2 Hebrew letters as well. It was a notational nightmare. I will not say more because this is being recorded. All right. The change of variable formula is very important, but it can get messy. Fortunately, there are a couple of cases that are extremely valuable that we can isolate that have really nice conversions. And that's what I want to focus on. So I want to start with the following motivation. And I will talk about how I made a mistake when I was preparing this lecture and lost a lot of time. So imagine you have a solid sphere of uniform density. And you have a point without loss of generality because it's so symmetric. Let's say the point is directly above the North Pole. And you want to calculate the force of gravity. So for the purposes of today's lecture, we will assume Newton is correct and Einstein does not exist, that gravity is given by a 1 over r squared force, that every 2 objects in the universe pull at each other. Right? No general relativity today, my apologies. We want to calculate what is the force on this object. What this means is for every point on the sphere, we have the sphere is x squared plus y squared plus z squared. Let's just make it a unit sphere to make things a little bit nicer. So we want to calculate what's the force. So we'll say this is M1. We need a density. What letter do you normally use for density? Who here remembers their science classes? Yes?
Capital D.
You use capital D for density?
Didn't we use rho?
Usually use rho for density.
Okay.
We can't use rho because if we're going to go to spherical coordinates, rho will be needed for that. We don't want to use d because d looks like derivatives. I'll use B for Back to the Future and George McFly. Right? So we will say it has a density. So if I want to calculate what the mass is, since it's constant, the mass would be the integral over the sphere of just B dx dy dz. So if I have a small little bit, the mass of that little bit would just be B dx dy dz. So for each point in the sphere, I can calculate the force. And so if I'm at the point x, y, z, let's say this is at the point 0, 0, r. The distance that this is going to be will be this point minus that point. Now, because of the symmetry of the sphere, whenever 2 masses are attracting each other, the force of attraction is along the line connecting them. But because of symmetry, if this point is pulling us to my right, the corresponding point on this side is pulling us to the left. And the net effect is only the downward pull. So everything else cancels. So all that would really matter is I would need to figure out what is this angle over here. I'll call that alpha. And then I would have to weight the force by the cosine of that. So my force would be G m1, my infinitesimal volume, which would be b dx, dy, dz, divided by the square of the distance between them. So it would be x squared plus y squared plus z minus r squared. Fortunately, we need r squared, so that's perfect. But now we need to have the cosine of the angle. So if you want to think about what's going on, so here is our angle alpha. This whole thing is r. This is at the point x, y, z. This is at the point 0, 0, r. How would we find that angle? Yes?
Use spherical coordinates.
We could use spherical coordinates. And if we use spherical coordinates, then we would be having this in terms of theta and phi. Right now, I don't want to do spherical coordinates because that would make your life pleasant. And I want to just show you how bad this calculation is to motivate why we will pay attention and learn the change of variable formula. How could we find that angle? And actually, I don't need the angle. What do I need?
The sides.
Nope. I need the cosine of the angle. Right? I don't need the angle itself. What could I do to find the cosine of the angle? Do we know any formulas that give us a cosine of an angle?
Dot product.
The dot product. So if I take these two vectors, so this is the vector 0, 0, r, this is the vector x, y, z. I can calculate this vector here. I can take the dot product of those two vectors. So my vector v1 will be 0, 0, r. My vector v2 will be x, y, z minus r. That might be off by minus, I don't really care. Yeah, I think this should be a negative r. Because we're using this as the starting point. So I do 0, 0, 0 minus this. I would do x, y, z minus this. So then v1 dotted with v2 is going to be the length of v1, the length of v2, times the cosine of the angle between them. Well, the length of v1 is just going to be r. The length of v2, hey, that's this expression. That's the square root of that. So then I need to multiply this by the cosine of alpha. So that's going to be v1's length, v2's length, divided by, I'm sorry, this should be in the denominator. v1's length, v2's length, and then v1 dotted with v2. That's the integrand. Then we have to integrate this, and we have to find what's the bounds of integration. Okay, so I will let you do the substitution. It's not going to be horrible, because the length of v1 is just going to give us a little r. Great, that's something like what we want. The length of v2 is going to give us the square root of this. Well, something like this, maybe the maybe 5/2 power, something like that. So now, what's the bounds of integration? So x goes from -1 to 1. Then y will go from minus the square root of 1 minus x squared to the square root of 1 minus x squared. And then z will go from negative square root of 1 minus x squared minus y squared to the square root of 1 minus x squared minus y squared. So, now we have to think about this. What are we integrating over here? So do I have the bounds right? I've got a sphere of unit length, but I want to get not just the points on the boundary. I want to get any point as well. And so over here, I'm letting x go from -1 to 1. Okay, well, that seems to make sense for each value of x. Once I choose a value of x, then I have to look at how far can y go, how far can z go. And I want x squared plus y squared plus z squared to be at most 1. Well, the largest value is going to be at the extreme end, if z gets this large. So if I look at x squared plus y squared plus z squared, it will be at most 1. And if z is a little bit less than that, it'll be inside. So this should cover all the points in my sphere. So as a nice painful exercise, write this down explicitly and try to evaluate this integral. The remarkable fact is that when you do this and the dust settles, it's equivalent as if all the mass of the sphere was at the center. This is an incredible simplification. To be able to say, if you have a spherical object, all the mass is at the center. It makes these problems far easier. If you're trying to calculate the orbit of the planets around the sun, or the moons around the planets, not to have to do integration like this every single time is phenomenal. But when you look at what's going on here, this is a very painful integral to do. Now, there's a lot of symmetries in this integral. And that's the whole point of spherical and polar change of variables, is we want to exploit those symmetries. Okay? I tried to simplify the argument a little bit, and I tried to say, well, what if instead of doing this painful integral, what if I just say, let's do a circle, and imagine we have the mass up here, and calculate what is the net force if we just had a circle. Can we say that that's the same as if all the circle's mass is concentrated at the center? Because if we can do that, then we can just spin the circle. And I tried this for a while, yesterday, and it just did not work. And the reason it didn't work is because it's false. It's not, you don't have the result that if you have a circle, it's the same as if all the mass was at the center. And here's the simplest way I could say, let's keep trying to do these symmetries. Let's imagine I have just two little pieces of mass exactly opposite each other. And I want to calculate what's the force. Is it the same as if all the mass was at the center? Well, let's say that this is 0. Let's say this is +1, this is +2, and this is -1. We'll put a mass of 1 kilogram at each of these points. So what's going to be the force from this one? The 1 over r squared is going to be 1. And then 1 over r squared, the distance from down to here will be 3, so it'll be 1/9. So we'll get 10/9. If I put all the mass at the center, that would be mass of size 2. And the distance is now 4, so it would be 1/4, which is 1/2. So they're not equal. So I can't just make the simplification. If I have two masses, it's equivalent to a doubled mass in the center. I can't make the simplification that if I have a circle, it's equivalent as if all the mass is at the center. But with a sphere, I can. And it comes down to how the points are distributed. How many points you have up high, how many points you have down low. Okay? And then, did I give you guys the heuristic as to why gravity is a 1 over r squared force? Looking at the surface area of the sphere. The surface area grows like the radius squared. So if the force drops off like 1 over r squared, that's going to give you a nice constant. All right, so this is hopefully motivating why you do not want to integrate like this, why you want to learn the change of variable formula. If you ever think that the lecture is bad, please go back, write this down carefully, look at the integral, and try to do it. You are welcome to use Mathematica to do this. You are welcome to use any program you want to try to do this. It is a terrible, terrible integral to do. When you put it in spherical coordinates, it becomes very fast, and we can do it very easily. One nice thing which is worth remembering is the dot product which gave us the law of cosines, which gave us the cosine of the angle, is extremely useful and allowed us to express the cosine nicely. So you want to remember sometimes in math what's being asked. We don't need to find alpha. We didn't need to find that angle. We only needed to find its cosine. This is very similar to when we did Lagrange multipliers. We don't necessarily need to find that lambda. It's just useful to help. So let's do polar coordinates first. All right, so have you seen polar coordinates? Okay. So you have x is our cosine theta, y is our sine theta. I prefer polar coordinates to spherical coordinates because I was a double geek. I have undergraduate majors in math and physics, and the physicists and the mathematicians have different conventions for spherical coordinates in terms of what is the angle theta, what is the angle phi. Everybody agrees what the angle should be in polar coordinates. But when you look at books for spherical coordinates, you've got to be very careful. Different books will label things differently. We have the beautiful relation, x squared plus y squared is r squared. And so the idea is we want to figure out how to calculate integrals in polar coordinates. Now, a circle in Cartesian, if I give you x squared plus y squared is less than or equal to r, that's what it looks like in Cartesian coordinates. In polar coordinates, well, this is just now r is less than or equal to r, and 0 less than or equal to theta less than or equal to 2 pi. So in polar coordinates, a circle is actually going to just be a rectangle. Well, with rectangles, it's very easy to interchange orders of integration. Theta goes from 0 to 2 pi, r goes from 0 to r. I can switch the orders. Remember the problem we saw earlier today? We had a triangle region. The bounds of integration change depending on the order we do them. What's nice is about rectangular regions, the bounds of integration don't change. They're the same no matter how you write them. So it makes the integration a lot nicer to be in the rectangular setting. All right. So we want to figure out, we have the little area element dx dy, and we want to figure out how does that convert into di d theta. And what we'll see is we need to put in an r over here. And we talked a little bit in the past that you should really view this as dr times r d theta. And the reason you should view it as an r d theta is not united. If you want to put x and y in meters, r is in meters, this will be meters squared. That's an area, that's great. But dr d theta would only be in meters. R d theta is the length of an arc. D theta is the angular measurement. So this will now give you something of units of meters. So really, we should write it or view it as dr times r d theta. But when you're going to integrate, you want all the r's together, you want all the thetas together. So you would put the r over here, and you'll do it as r dr. But in terms of trying to understand what's going on, where is it coming from, this is where it's coming from. All right. So let's draw a circle. So on pi day, we proved the area of the circle, we proved the perimeter of the circle. All right. So let's start off with a circle of radius r. I'm going to start off at some angle theta. And then I'm going to increase my angle, and I'm going to increase my r a little bit. So this increase over here will be delta r. This increase over here will be delta theta. This is not drawn to scale. These are supposed to be very small increases. And I want to figure out what is the area of that small segment. That's corresponding to my little change in r, my little change in theta. Well, what's the area of the whole big circle?
Pi r squared.
Not pi r squared. Close, but not quite pi r squared. The whole big outer circle. Yes?
Pi r plus delta r squared.
R plus delta r. That's the area of the whole big circle. If I subtract the area of the smallest circle, then I'll get the area of the ring. So now I subtract pi r squared, and that's going to be the area of the ring. Now I want only part of the ring. What fraction of the ring is that?
Delta theta over 360.
Almost. Not 360. Not in this class.
2 pi.
Over 2 pi, right? As soon as we start doing calculus, we have to work in radians. So what fraction do we have? It'll be delta theta, the change in angle, out of 2 pi, the total possible angular measurement. And this makes sense. If delta theta was actually 2 pi, if we had the whole circle, we'd get it all back. So now we just do some algebra. So when we expand this out, r squared will cancel the r squared, and you'll get pi, or 2 pi r delta r, plus pi delta r squared, times delta theta over 2 pi. Right, the 2 pi cancels, and so the first term becomes r delta theta, and the second term is going to become 1/2 delta r squared delta theta. And now if we take the limit as delta r and delta theta go to 0, you can see this piece is looking like the r dr d theta. This piece is looking like 1/2 dr squared d theta. So this is a slight abuse of notation. But essentially, this term is insignificant in the limit because we're doing a double integral. So we integrate over delta r, we integrate over delta theta, but this is going to have an extra delta r floating around. And so because this is a third order thing, and we're only doing 2 integrations, one survives. And it becomes insignificant in the limit. So as delta theta and delta r get smaller and smaller and smaller, this piece is negligible relative to that piece. And so in the limit, we get that the infinitesimal area element is r dr d theta. Okay? If you wanted to just try to estimate this and say that little arc is approximately a rectangle, it's not, but it's not a terrible approximation to say it's a rectangle. We've got, our circular arcs like this. This is the radius r. This is the radius, I'm sorry. This is coming from a radius of r, this is coming from a radius of r plus delta r. Approximately how thick is this?
Delta r.
Delta r. And now the whole reason we use radians is the arc measurement is the radius times the angle. So since the angle is delta theta and the radius is r, this length over here is r delta theta. This one over here is r plus delta r times delta theta. So while it's not quite a rectangle, when delta r is extremely small, the difference is so small, it's really well approximated by a rectangle. And then you're going to have r delta theta times delta r, and there's your r dr d theta again. So lots of different ways of seeing r dr d theta. Let's do one more way of seeing why it's r dr d theta, because this is so important. And this last way is the way that's going to generalize very nicely for the other change of variables. So we're going to have, say, our xy space, and we're going to have our uv space. So I'm going to do things in a little bit more generality, and then later we will replace things in terms of x and y. Okay? So what this means is I have some way of going back and forth between these coordinates. I can write things in xy, I can write things in uv. If uv is r theta, then I've got the relation x equals r cosine theta, y equals r sine theta, or r equals the square root of x squared plus y squared, theta is the arctangent of y over x. I've got these relations going back and forth. Okay. So imagine, I'm going to try to do it better. Set up with t. There's 2 ways to do this. So I'll say I have t of xy is going to give me u of xy, v of xy. So t will be my transformation that you start with your x and y as your input, and you get your u and v coordinates as output. You could go the other way. You can start off with u and v and get x of u and v and y of u and v. Okay? So now, let's imagine I start at some point x0 and y0. I can take t of that, and that'll be my point u naught v naught. I now want to see what happens if I change x by a little bit. So I want to look at t of x naught plus delta x, y. Or I could change y by a little bit. I could be at t at x naught, y naught plus delta y. Or I could change them both and have t x naught plus delta x, y naught plus delta y. So how do I expect this to be? Well, t of xy is u of xy, v of xy. I'm increasing x by delta x. So this is the point u of x naught plus delta x, y, comma, v of x naught plus delta x, y. So what do you think u of x naught plus delta x, y would be? How would we approximate that? If delta x was 0, what would this be? That would just be our point u naught v naught. So this should be u naught plus a small little change, plus partial u with respect to x times delta x. So this is just the tangent line approximation. This is just the first order approximation. Where am I? I'm where I started, plus my instantaneous speed times the elapsed time. Over here, I would get v naught plus dv dx delta x. If I came over here, I would have the point u naught plus du dy delta y, and then v naught plus dv dy delta y. We'll do this in more detail later, but this is a parallelogram. How would you find the area of a parallelogram? So if I give you two vectors, all this stuff from chapter 11, yes?
Cross product.
Cross product. Or determinant. So you can take these vectors in 2 space, bump them up to 3 space, and take the cross product. But we also did, and it was very similar, it was related to this, if I have two vectors, the area of the parallelogram is the determinant of the matrix. So what is this vector? Well, they both start at u naught, v naught. So in this direction, what's the length of this vector, or what's the angle? It's du dx delta x, dv dx delta x. Because I just want to look at what's this length of this, what's this vector, its length and its direction. So when I subtract, because they all start with u naught and u naught, they cancel. What about this direction? I will get du dy delta y, comma, dv dy delta y. And so now I would calculate the determinant. I would get du dx delta x, dv dx delta x, du dy delta y, dv dy delta y. And so it's this times this minus this times this. So we get du dx dv dy minus dv dx du dy times delta x delta y. Because each term has a delta x, each term has a delta y. This is my original area. And so this should basically be my du dv. So unfortunately, I think I did things backwards. If I want polar coordinates, I think I actually want to make x and y be r and theta, and I think I want to make u and v x and y. But this tells us how things would be related. So let's end by looking at polar coordinates. So x equals r cosine theta, y equals r sine theta. So I can write x as a function of r and theta as r cosine theta. I can write y as a function of r and theta as r sine theta. So unfortunately, flipping the roles of u and v and x and y, I would get dx dy would equal dx dr dy dy d theta minus dy dr dx d theta dr d theta. All right. What's the derivative of x with respect to r? So I've got x is r cosine theta. What's the derivative of x with respect to r? So derivative of x with respect to r, what do we get?
Cosine theta.
Just cosine theta. What's the derivative of y with respect to theta? It's derivative of r sine theta. So what would that derivative be?
Sine theta.
Almost. So we're taking the derivative of this with respect to theta.
Oh, okay.
So what would be the derivative of r sine theta with respect to theta?
R cosine theta?
R cosine theta. Now we subtract off the derivative of y with respect to r. What's the derivative of y with respect to r? That's just sine theta. Then we take the derivative of x with respect to theta. The derivative of cosine is minus sine. The minus reinforces with the minus becomes plus. We get r sine theta, dr d theta. And now look, we get cosine squared r plus sine squared r. Oh, that's just r. And we get r dr d theta. So our third way of seeing why polar coordinates works. We're going to see this again. But this is the way that really generalizes. We start off with a transformation. You give me an x and y, I give you a u and a v. If I change my x and y a little bit, where do I change things? Well, in the xy space, I should basically be having just a little rectangle, delta x, delta y. How is that going to look in my uv space? And so the square is going to be approximately a parallelogram. It would be a perfect parallelogram if you had a straight line here and a straight line here. We don't quite have that. If we actually wanted to expand this point, it really would be the sum of these. And everything will work out nicely, because now it's moving in both of them. So we would have u naught plus du dx delta x plus and all the y's as well, because they're both moving. So this is the real way to look at what's going on. This is where the change of variables comes from. It's how does a small infinitesimal square or rectangle transform? It transforms to a parallelogram. We use the tangent line approximations to say what's going on, and that will give us the new thing. We then calculate the area of the parallelogram by using the determinant. So this tells you if we have something like spherical coordinates, we're going to have not a parallelogram, but a parallelepiped. And we'll have to do a determinant of a three-dimensional object. So it becomes a little bit more involved. So this is where what class would be useful? Linear algebra. Actually knowing what a matrix is, knowing how to work with matrices, knowing how to calculate determinants, understanding vectors, that would be a lot more useful. This is why, when I was a freshman, we actually had a unified year-long class where you did linear algebra for a little bit, then pause. Now apply that linear algebra to do calculus because you now have the right language to do things. And then pause, go back and develop more linear algebra, and just go back and forth. The disadvantage is if you decide math is not for you, you have done half of linear algebra and half of multivariable calculus at the end of the fall, and you are screwed for future classes. You can't go to multi, you can't go to linear. You don't have the prerequisites for any class that requires either one of them. So it's really a year-long commitment. But in a situation like this, the dividends are enormous. So now we can do polar change of variables. So if I give you your various problems which we've looked at, they are now much, much easier to do if we have this. So let's just try one. So let's integrate x goes from -1 to 1, integrate y goes from negative square root of 1 minus x squared to the square root of 1 minus x squared. I'm just going to make something up right now. dt x squared plus y squared dx dy. Yeah, good luck integrating that. Right? We would need to find a function. If I integrate first with respect to y, whose derivative is e to the y squared, can't do it. But we're integrating over a circle. So let's change variables. So this is the same as integrating r goes from 0 to 1, theta goes from 0 to 2 pi. Or actually, no, I guess we write theta outside. Theta goes from 0 to 2 pi. In polar coordinates, what is x squared plus y squared? R squared. And what does dx dy become? R d theta. R dr d theta. Oh, this integral now is very nice to do. So this is actually related to one of the most important integrals in all of mathematics. So what I'll do is I will end the day by just doing this one. So I was kind of motivating it by just starting with that first. The normal distribution with mean mu and variance sigma has density 1 over the square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. So a lot of things in the world are normally distributed. And for probability distribution, you have to be non-negative and you have to integrate to 1. This is clearly non-negative, but integrating to 1 is a bit of a challenge. I'm going to do the special case, mu equals 0, sigma equals 1. So I'm just changing notation so that the average value is 0. This will not be what the next exam will be. And the standard deviation is 1. So I need to prove that the integral from x goes from negative infinity to infinity of 1 over the square root of 2 pi e to the negative x squared dx, I want to show that equals 1. Okay? We don't have that much time, so I'm going to go fast. Let's call that integral I. I'm going to square the integral. So I'm going to write it again. And I'm going to write it now using the letter y. 1 over the square root of 2 pi e to the negative y squared dy. I can't use the same letter x. I'm using a different dummy variable. This is sometimes it's better to take one step backwards to then take 2 steps forward. You give me a one-dimensional integral, I'm going to convert it to a two-dimensional integral and take the square root. The reason is we can now use multivariable calculus to evaluate a one-dimensional integral. So now, this is the same as the 1 over square root of 2 pi, they all come out, they reinforce. The integral x goes from minus infinity to infinity. The integral y goes from minus infinity to infinity. And then we have e to the negative x squared plus y squared dx dy. Switching the order of integration will not help us because it's symmetric in x and y. If you switch the orders of integration, there's no help. So clearly switching is not going to help. What's the only thing left we can try? Polar. And so now, theta goes from 0 to 2 pi, r goes from 0 to infinity, e to the negative r squared, r dr d theta. We have a 1 over 2 pi. Oh, great. When we do the theta integration, what do we get? When you integrate with respect to theta, there's no theta dependence here. What do you get? Not 0. The integral is just 1. So we have 1 over 2 pi. The theta integral is 0 to 2 pi of d theta. And then the r integral, 0 to infinity of e to the negative r squared r dr. What's the theta integral going to give you? It'll just be
Theta.
not theta. You're integrating, right, it'll be theta, then you evaluate 2 pi and 0, you get 2 pi, which cancels the 2 pi out here. So you're left with the integral r goes from 0 to infinity, e to the negative r squared r dr. Well, if I put a 2 over here and a 1/2, that's the right antiderivative, right? And so what do we get? We would get 1/2 e to the negative r squared. I have a minus sign, so that flips the order of integration, 0 infinity. And actually, this is giving us a 1/2. Oh, I dropped the 2. It should be x squared over 2, y squared over 2, over 2, over 2, over 2. So we don't actually need the 1/2, because it works out perfectly. And we get 1. And this is why pi shows up in the Gaussian in all that statistics. It's coming from polar integration, which you would not see when you first look at this. All right, so this is a good place to stop. We did a lot today. We reviewed some basic stuff. We did the polar coordinates. And now we have 3 different reasons why polar is true. And now we can begin to see what you can do with this. This was a one-dimensional integral that we cannot do. And we can solve this one-dimensional integral by multivariable calculus.